All right, welcome back to Calculus. We're going to continue our work in section 8.3, looking at applications of the definite integral. Today I'm going to tell you about centroids, or centers of mass. So you can see the outline here. I want to discuss some of the technicalities of computing this stuff, things that physicists call moments. Centroids, or centers of mass. We'll talk about one-dimensional and two-dimensional discrete systems to begin with. That's going to be our kind of local estimate. So I want to give you an idea of what kind of physics problem we're solving and do those discrete versions of it with no calculus, but those are our local estimates. And then we'll use those local estimates to derive some integrals for those same things, moments and centroids, for two-dimensional continuous systems, where everywhere we're going to be assuming that we have a constant density throughout our two-dimensional region. Okay. So let's get going here. I'm going to do something that I don't do very often. In fact, maybe I've never done it, but I'm going to stop the screen share and turn on my camera because I want to show you something with this prop that I have that illustrates what it is that we're trying to solve. So what do I mean by a two-dimensional region? I've got one here. I made one for you. It's a rectangle. This rectangle is made out of cardboard, so it has some thickness to it, but I'm totally ignoring that. Okay, so I'm only considering it as a two-dimensional mathematical object. And by its centroid, I've marked it there in the middle, the dot. Ignore the notation, we'll talk about it later. But by its centroid, I mean a point in that region upon which the region would balance. I'm kind of shaky here in my finger, but I'm putting my finger right on that dot where I've marked. I can't show you from the angle because it'll fall off, but it's the balance point. I've drawn two lines through here. How did I find that point? It's a rectangle. It's the center of a rectangle. The center is the point where it would balance. If you take a line perpendicular to two of the sides or parallel to two of the sides through that center, it balances along that line. Sorry about that. It balances along that line. It balances along the other one. Yeah, those are lines just straight down the middle of the rectangle. So if it balances across those two lines, it balances at the point. And you don't need calculus to find the centroid of a rectangle because a rectangle is a simple geometric shape. But what about more interesting shapes? Yeah, like what about this one that looks not unlike the great state of Idaho? If I think of it as a two-dimensional region, again, completely ignoring the thickness, just thinking of it as a two-dimensional region, it has a centroid. It has a point that you can balance that region on. And what I want to show you in this section for our second application in physics, if we take regions like this, describe them by functions, in our analytic coordinate plane, how could we derive Riemann integrals to calculate the coordinates of this balance point? That's what I want to show you how to do. Okay, balance points are cool. Before we leave and go back to the usual whiteboard, you know this. If you take them as an axis of rotation, objects spin very well. Even three-dimensional objects have centroids. Here we're talking about 2D, but they spin very well around their centroids because the mass of the object is in some sense equally balanced around that center of balance, that centroid. So it's very fluid spinning motion, although it's not completely fluid here because I've just approximated the shape or the spot. Didn't do actually any measurements, I did that by eye. Watch my state of Idaho spinning around its centroid, very fluid, still a little wobbly, but again, I did it by eye. But watch, I'm taking a point way away from the centroid. See, that's very wobbly. The mass isn't spread around that point very well at all. Sorry, I can't keep it on my pen there very well. Okay, so that's it. That's enough of looking at me. Let's go back to the usual, share that screen and start our work. Start trying to answer the question, how are we going to find those points? How are we going to find that centroid? So let's see if I can talk my iPad into coming back live. Not sure what you were seeing there, but good. So let's get going. Let's talk about the one-dimensional discrete version of this problem. Sounds kind of intimidating. What do I mean by that? Suppose by discrete system, I have a couple of masses. Suppose I have two masses. I'm going to drop the units out of the conversation, but everywhere just think grams if you want. The masses are in grams if you want to be measuring things. We'll measure masses in grams or kilograms, whatever you like, whatever your favorite unit of mass is. But by a discrete system, I just have some finite number. In particular, here I have two. And I've got them attached at the end of this stiff object, this teeter-totter, if you want. And the balance point, it's often called a fulcrum, is a place where that would be parallel to the ground. Yeah, so I'm looking for the point of balance. And there's a physical principle that says that that system will balance if you take the two distances, d1 and d2, between the masses and the fulcrum. If the product of the mass with the corresponding distance, if those products, excuse me, are equal, then the system will balance. And if it balances, those products will be equal. Okay, so if I have two masses located d1 and d2 units apart, are away from the fulcrum, then this system balances if and only if that equation holds. Taking that from physics. So let's coordinatize this problem. Let me just scroll down here a little bit. I've got the same picture here. So I've got my stiff teeter-totter between my two masses. Here's my fulcrum. If I coordinatize it, I'm just giving myself this number line down here. All right, so the number line has an origin somewhere. I just marked it right there. It can be anywhere on the number line. And then these distances I'm talking about are measured from that origin. So it's reasonable notation. Let's say that mass 1 is located at a point called x1. Mass 2 is at x2. And then this is, because of the bar in statistics usually means average, but and also in this setting, it means center of balance. So I'm going to denote by x bar the x coordinate of the fulcrum. Yeah, so my goal would be given m1, m2, x1, and x2, how do I find x bar? Let me write that down. That's our goal. So we're given the two masses, m1 and m2. We're given their locations, x1 and x2. We'd like to find x bar. I'd like to find the point where the system balances. So let's just read through what I've got here. I said it balances if and only if those two products are equal. But we've talked about this a lot. In the coordinate system, d2 is x2 minus x1. Remember, you subtract the smaller number from the bigger one. That's the distance. It's the theme of our class. d1 is x bar minus x1. So I'm just plugging those in. Okay, then you can just follow the algebra. I distributed the m's on both sides. And then what did I do? Maybe this line I can put in a little bit of a detail if you want. On the left-hand side, I factored out the x bar. Yeah, so I have x bar times m1 plus m2, the sum of the two masses. So there's a little extra detail for you on that line. So if x bar times that sum is equal to this thing, well, just divide both sides and you get that last equation. And there we've accomplished our goal. We've got x bar, and look what it's in terms of. It's in terms of m1 and m2, x1 and x2. It's perfect. It's exactly in terms of what we're given. So that's how you find the centroid of a a one-dimensional discrete system with two masses anyway. All right, so you have some homework problems like that. I'm not going to do an example with specific masses and x's in here because it's an arithmetic calculation, but you can ask me about it if you get stuck in any of the homework. Here's some terminology, so we could talk to each other about this stuff. This terminology comes from physics, so we're going to adopt it and use it because it's standard. So these numbers, these products, m1 and m2, m1 x1 and m2 x2, the product of the mass with the coordinate of it in our coordinate system, those are called moments, moments about the origin, all right? Maybe in an office hour conversation, we can talk about what they sort of mean. They kind of give you information about the system's a tendency to tip in a certain direction. Okay, but they're called the moments. When you add them together, that's called the total moment. So the sum of all the moments, there were two of them, it's called the total moment. This one needs no explanation. M1 plus M2 is called the total mass of the system. Okay, a little bit more general than what I drew a picture of, but if you take any number of masses and they're located at places in some coordinate system, then these products are still called moments, and if you add them all together, that's the total moment. The sum of all the masses is the total mass, and it's true that that ratio always gives you the coordinate of the centroid. So that's where your system is going to balance in 1D. So if you took some bar and you placed it on that bar in n locations, x1, x2 up to xn, little weights, masses, m1 through mn, then the way you've measured distances, this will tell you where to balance that bar. Nice. Okay, we've got to move along here. Stop the video and take a break if you need to, but let's talk about the two-dimensional system. In the two-dimensional system, I'm dropping weights not at points on a number line, but at points in the plane. I have two number axes, x and y. All right. But I can consider this as a couple of one-dimensional systems, right? Because if I think about the x-axis and the number line, if I just think about these weights as being placed on the x-axis, well, their x-coordinates are the locations and the weights are the weights. So I would have moments, and I'm going to call those moments about the y-axis. Because when you're thinking about those x-coordinates, when you're thinking about the weights being at the corresponding points on the x-axis, then that's the moment about the origin, but the origin with respect to the x-axis, yeah? So you're going to be looking for the fulcrum, and that fulcrum would balance in something parallel to the y-axis, so hence the name. And likewise, if you think of those weights as being as points on the y-axis, you also get some moments. Sorry, I skipped the top one. But there, the y-coordinate is what's telling you the location. So you're going to multiply the mass by the y-coordinate. And we're going to call that the moment about the x-axis. So here's its notation. M sub x, moment about the x-axis. M sub y, moment about the y-axis. Those formulas are how you compute them. Again, remember, you're given the mi's and the xi's. You're given the mi's and the xi's. Right? You want to find the centroid, x bar, y bar. It has two coordinates because it's a point in the plane. But all you do to find x bar, well, you take the moment about the y-axis and divide it by the total mass, just like we did in the 1D system. To do y bar, you take the moment about the x-axis and multiply and divide it by the mass. So there's a little bit of something to get used to. Yeah, x bar is moment about the y, but that's because it balances, in the x direction. Same for y bar. Nice. Here I didn't say it, but the total mass is what I'm denoting by m. It's just the sum of the mi's. So it's like two one-dimensional systems, one for x, one for y. Nice. One takeaway from these formulas that I want to look at very carefully, I'm going to kind of box these things because they're important. If you just take those equations for x bar and y bar above and solve them, quote unquote, for the moments, m sub y and m sub x, you get those lower boxed formulas. Yeah. So one interpretation of what these lower box formulas are saying is if you took a single mass with total mass of the system, and you put it at the centroid, one mass at one point, you get the same moments as the original system. All right. So in other words, when I'm kind of thinking locally, I can just assume that all of the mass of my system is at one point, and I wouldn't change the moments. If I were just trying to calculate moments, that assumption won't cause me any error. Stop the video and let that kind of sink in for a second. Let's keep going. In the video, if it's still moving, I'm still going. So one last thing before we can do our Riemann integral. If you have a constant density, which we're going to make that assumption throughout. So really there's no harm in even setting it equal to some constant. One is sort of convenient, but all I mean by that is that when you take some region in the plane, its density at one point is not different than it is at any other point. So it has the same density, say grams per square centimeter throughout all points. So that's going to be an assumption that I make throughout this, that the density is constant throughout this region. Right now it's a rectangular region. We've said the center of the rectangle is its centroid. Okay, so we've already talked about that. If you want to find the centroid of a rectangle, it's the point that is equidistant from both sets of parallel sides. The mass of that rectangle, well, you would take the density and multiply it by its area, right? If I put in some units just to make that a little bit more concrete, if you took something like grams per square centimeter and you multiplied it by square centimeters, well, then you're going to get grams. Right, so the mass of that thing would just be its density times its area. And let's write down what our equations up there told us. What equations am I talking about? These lower red box ones, that when you take the mass times the coordinate of the centroid, x or y, you get the appropriate moment. So I just want to write that down here in the context of this rectangle. If I take the mass of the rectangle, that is rho times its area, and I multiply that by the x-coordinate of the centroid, that is the point that's marked there, then I'm going to get the moment about the y-axis in this coordinate system. And likewise, if I take rho times the area, that is the mass, and I multiply it by y bar, then I'm going to get the moment for the x-axis. So I'm going to use these things in just a moment to make local estimates for the moment about the y-axis and the moment about the x-axis. Okay, so here we go. We're into our final situation. I've got a region in the plane bounded by a function, f of x, over an interval from a to b, the usual setup. It has a constant density, rho, okay, grams per square centimeter if you like. And what's the mass of that region? I want to start with that. The mass of that region would just be the density times the area, yeah? So the density of the region times the area of the region is just the integral of f of x dx. So we compute the mass of that region in the same way we do for the rectangle. It's just the area is computed with an integral. So the mass is just the density times the integral of f of x dx from a to b. So let's make a local estimate for the moment about the y-axis. Okay, so look down here in this picture. I'm looking at just this one rectangle, right? So I'm cutting the region up into a bunch of rectangles, usual Riemann sum kind of thinking, and I'm just looking at this one. And I am going to use this picture. It's a little bit hard to see, but the author, what you need to look at is the author's telling us the centroid of the rectangle's coordinates right there. I'm going to write it so it's a little bit easier to see. He's writing it xi, I is because of the sum, bar because it's a centroid, and then it's a rectangle. The height of it is f of xi bar, so you take half of that to find its midpoint. Okay, so that's what you really need from this picture, is that this point right there, its coordinates are written above there, xi bar, 1/2 of xi bar. And I can assume that as far as that rectangle goes, the entire mass of that rectangle is concentrated at that point. Okay, what's the mass of that rectangle? Well, like we were just saying, the mass is the density times the area. The area of the rectangle is its height times its width, f of xi bar times delta x. And if I multiply that mass by the x-coordinate of the centroid, the midpoint there, xi bar, then I'm going to get the moment about the y-axis. I'm saying it's a local estimate because the rectangle just approximates the area under the region. It's not exactly equal to it. So you add those things together, you'd get the moment for each. This is a physical principle. If you took the moment for each one of these rectangles separately, you can just think of them as weights, if you like. If you concentrate their masses at points, it's the same principle as before. So the total moment is the sum. Take the limit as delta x goes to 0, more and more rectangles, and we get this integral. All right, so that's kind of our first major result with the one above about the mass. The mass of the rectangle is the integral of the density times the area. Well, here's how you compute the moment about the y-axis. The moment about the y-axis is the integral of the density times x times f of x, all right? Integration by parts is frequently used. Okay, I'm going to just keep going. This video is kind of long. If we wanted to make a local estimate for the moment about the x-axis, I'm going to think the same thing. I'm going to take the mass, it's the same as above, but I multiply it by the y-coordinate of the centroid. That's our 1/2 f of xi bar. So I didn't write the Riemann sum this time, but there's your integral. You want to find the moment about the x-axis, then you integrate from a to b 1/2 of rho times f of x squared. Where's the f of x squared come from? It comes from one factor of f of x there and the mass, and the other factors from the centroid. So to summarize that, given some function, let me just tell you what you're given, and we're going to do a couple of examples. Given a function, y equals f of x, and you're going to assume that you have constant mass density. Then to compute the mass of that thing, you integrate the density times the function value. To compute the moment about the y-axis, you integrate the density times x times the function value. And to compute the moment about the x-axis, you compute, 1/2 rho times f function value squared. So you compute 3 integrals, okay? You compute the mass, the moment about the y, the moment about the x. And then you find the coordinates of the centroid by assembling in the same way you do for the discrete system. The x-coordinate is my over m, the y-coordinate is mx over m. Okay, pause the video, take a break. I'm going to take a drink of water and let's do a couple of examples. I'm going to try to make these kind of quick. This is getting long, and so I won't dwell on the integration steps here too much. I just kind of want to show you the process. So this time, let's draw a picture. We got a function that looks like square root of 25 minus x squared over the interval from -5 to 5. No fancy computer-generated picture here. You can stop the video and plot it on Desmos. That's a semicircle. It's the upper half of a circle of radius 5. Okay, so the interval from -5 to 5 is precisely the portion over the x-axis that semicircle lives. And I can see from symmetry that the x-coordinate of that is equal to 0. The x-coordinate of the centroid is equal to 0 because this shape is symmetric about the y-axis. What it looks like over here and over here are exactly the same. So I know it's got a balance along the line x equals 0. So what we need to do is find y bar. So I'm being a little strategic here. What do we need to know to find y bar? Here, that was a good scroll. I need to know mx and m. So those are the two integrals that we have to compute to complete this particular example. Let's do m first. So m is rho times the integral from -5 to 5 of our function value. Stop the video and think about how you're going to do that integral. How would you do that integral? Trig sub maybe is what came to mind. X equals 5 sine theta. It'll work. I'm actually going to take advantage of the fact, and maybe you thought this too, that that integral, ignoring rho, is giving me the area of that semicircle. And since it's a semicircle from geometry, I can tell you what its area is. It would be 25 pi. Well, that's the full circle over 2. So there's our mass. So we'll set that aside for a second. But yeah, 25 pi over 2 times rho is the mass of our region. So now what do we need? We need to compute m sub x. M sub x by the formulas that are above is equal to 1/2 rho times the integral from -5 to 5 of the function squared. So 25 minus x squared dx, because squaring the square root gets rid of it in a sense. And so, well, let's compute this integral. I don't have it computed out, so I'll just do it. First of all, I'm going to multiply by 2 and integrate from 0 to 5, again, by symmetry. Always trying to take advantage of symmetry if I can. 2 times 1/2 is 1. Antiderivative of that thing is 25x minus 1/3 x cubed, which I need to evaluate from 0 to 5. So I'm getting rho times 125 minus 1/3 of the same minus 0. So that's 2/3 of 125, or 250 over 3. And that's times rho. So we complete the calculation by saying, okay, well, y bar is what we just computed, mx over m. So that's 250 rho over 3 divided by, I got to scroll back to look at it. What was our m? Our m was 25 pi over 2 times rho. Notice that rho's cancel. It'll always be the case. So if you're only interested in not computing mx or my or m or just m, but you only x bar and y bar, you can always assume rho is 1, because in all the formulas, you're dividing one integral by another. Both have a factor of rho in them, which physically makes sense. You know, the location of the balance point shouldn't depend on the mass, right? If your like surface is made out of something with a very heavy mass density, you know, 20 grams per square centimeter, that wouldn't change where it balanced if it was only 1 gram per square centimeter. It would just change its weight. So the mass density doesn't affect the location of the centroid. Okay, so I was stalling. I should have been doing some arithmetic. There's some nice cancellation here. Maybe you guys have done it. How would it work? The 25 goes into 250, leaving 10. And then that 10 is over 2. So I think it should be something like 20 over 3 pi, if I'm not making an algebra mistake. I hope I'm not. I'm going to leave it as 20 over 3 pi. Okay, I don't have a decimal approximation for 20 over 3 pi. Maybe I could try to get one really quickly. You guys can do the same. So 20 over 3 pi on my calculator is approximately 2.1. 2.1. And that makes sense to me that it would be a little bit less than 2.5 because remember the circle has radius 5. So 2.5 is halfway, right? Continuing my crude picture. Certainly the centroid of the y-coordinate of the centroid is going to be a little below halfway because the circle's wider out here, right? So that contributes more mass. So that's going to pull the centroid closer to that edge in order to keep it balanced. So that matches my physical intuition. Okay, let's do one more. This time I'm taking a region, you can see it's bounded by 3x plus 1 over the interval from 0 to 1. And this time I think just to keep the video a little shorter, I'm going to set up these integrals with you and then let you compute the details. Okay, I'll give you the answers, but I'll let you compute the details. I promise there won't be anything more than polynomial here. So it's not a big ask to have you do this. Okay, but I just want to illustrate that we're given everything we need to know to compute the integrals that we need. So we need to compute the mass, all right? So the mass is rho times the integral from 0 to 1 in this case of just the function, 3x plus 1. Okay, so that's just the area under that line. You could do that with geometry if you wanted to. It's just a trapezoid. Then we need to compute the moment about the y-axis. That's the integral of rho times the integral from 0 to 1 of x times the height of the function. Okay, so that's rho times the integral from 0 to 1 of 3x squared plus x. So polynomial. Got to scroll a little bit here. You got to compute mx. mx is 1/2 rho integral from 0 to 1 of 3x plus 1 quantity squared. Okay, so that's 1/2 rho integral from 0 to 1 of 9x squared plus 6x plus 1. So polynomial. Polynomial. Please check these things. I'm going to try to read my notes carefully here so I don't write them down wrong, but I think if you check them, I'll write them in a distinct color. The first one should be 5/2. Okay, the moment about the y-axis, you should compute out to be, 5/2 rho. The next one should be 3/2 rho. And the last one, the moment about the x-axis, should be 7/2 rho. If I can read my own handwriting. So now that we have those three numbers, we can write down the coordinates of the centroid, right? So x bar, somehow memorize it, it's my over m, right? So the rows are going to cancel. Well, let me write them. So that's 3/2 rho over 5/2 rho, right? So that's 3/5, 0.6. Y bar is mx over m. Sorry about that. I'm getting tired. You're probably getting tired too. Mx over m. Okay, so that's 7/2 rho over again 5/2 rho. The rows cancel, so we get 7/5. Okay, or 1.4. Cool. So you're going to practice these things in your homework. Yeah, I hope that was useful. Thanks for listening. That was a long one.